I want you to picture a helicopter spooling up on helipad. You hear that escalating, deafening whine of the turbine.
Yeah, and you feel that physical punch of the rotor downwash just hitting your chest.
Exactly. It's an incredibly visceral experience.
Yeah.
And if you are like most people watching that machine, you probably carry a very logical, deeply ingrained assumption about how it takes flight.
Right, the intuition most people have.
Yeah, you assume that when the pilot needs to climb rapidly or, haul a heavier payload, they simply push a throttle, rev the engine, and spin those massive blades faster.
It makes intuitive sense. I mean, more speed equals more lift, right?
Right. But as it turns out, that assumption is entirely backward.
It's completely backward. It is a fundamental misunderstanding of the physics at play. The reality is far more rigid and, frankly, a much more impressive feat of engineering.
Which is the perfect setup for our mission today. We are doing a deep dive into this really fascinating document, metin6.txt, to uncover the high-stakes balancing act that keeps a helicopter in the sky.
Yeah, the text frames modern helicopter flight not just as generating thrust, but as a masterclass in managing absolute aerodynamic boundaries.
So we are going to break down the mechanics, the hidden automated systems, and the terrifying contingencies that all revolve around one mind-bending reality.
Which is why the rotational speed of those giant main blades never actually changes during flight.
Right. And if we connect this to the bigger picture for you listening, this text reveals how engineers have systematically conquered a series of aerodynamic paradoxes.
We are looking at a machine that is constantly trying to tear itself apart. It's constrained by the laws of thermodynamics on one end and the sound barrier on the other.
Okay, let's unpack this. Because to grasp why the rotor speed remains locked, we need to look at how lift is actually manipulated.
Exactly. The rotor system is essentially just a collection of rotating airfoils.
Like airplane wings spinning in a circle.
Yeah, precisely. And to get more lift, you don't spin them faster. You change the angle at which they slice through the air, the angle of attack.
Right, but the source text is incredibly strict about the limits of the rotor RPM, what aeronautical engineers call NOR.
Yes, NOR. It is a non-negotiable parameter.
So here's my question. Why can't a pilot just, spool the rotor up to, say, double the speed if they need to aggressively maneuver out of a dangerous situation?
Because they would instantly hit the transonic regime, which results in a catastrophic structural failure.
Oh, wow. So it just breaks apart.
It does. We have to remember that the tip of a rotor blade is moving significantly faster than the root near the hub. So if you simply increase the overall rotor speed, those blade tips will approach the speed of sound.
Right.
And when airfoil hits transonic speeds, the air physically cannot get out of the way fast enough. It compresses in front of the blade, forming these massive shock waves.
So the air essentially turns into a solid wall.
Exactly. This causes a phenomenon called compressibility. It creates an exponential spike in aerodynamic drag. But honestly, worse than the drag, the shock waves dramatically shift the center of pressure on the airfoil.
Which means what exactly for the machine?
It applies immense twisting forces or torsional loads to the blade. The blade grips, the pitch links, the rotor mast itself. None of these components are designed to survive the structural violence of transonic flight.
The rotor would literally tear itself to pieces.
Literally, yes.
And I imagine the other extreme is just as bad, right? Like, if the rotor speed drops too low, you don't just gently descend.
No, not at all. The blades reach their critical angle of attack, the smooth airflow detaches from the upper surface, and the entire rotor stalls.
The aircraft just falls out of the sky?
Exactly, it falls out of the sky.
So keeping that rotor speed constant, keeping NOTAR locked in that Goldilocks zone isn't just a matter of fuel efficiency. It is the fundamental prerequisite for survival.
It is the only condition under which the physics of rotary flight actually function. The entire aircraft is designed around servicing that single, constant rotational speed.
But, this introduces a massive mechanical conflict. If the pilot is maneuvering, climbing, or catching a harsh updraft, they are manipulating the collective pitch.
Right, meaning they are changing the angle of attack of all the blades simultaneously to grab more air.
But by doing that, they are inherently creating a massive spike in induced drag. So how do you pipe enough power to the rotor to fight off that sudden immense wall of drag without the engine overspeeding when the pilot lowers the collective again?
Well, that was the nightmare of early rotary aviation.
Really? How do they manage it?
In the early days, pilots had a manual throttle twist grip right on the collective lever. Every single time they pulled the collective to climb, adding aerodynamic drag, they had to manually twist the throttle at the exact same moment to roll on more fuel.
Wait, simultaneously?
Yes. If they didn't, that drag would pull the rotor speed down into a stall. And if they lowered the collective and didn't manually roll off the throttle, well, the unburdened rotor would overspeed into that transonic danger zone we just talked about.
You're essentially trying to perform complex calculus with your wrist while flying a machine in 3 dimensions. That cognitive and physical workload sounds totally unsustainable.
It was incredibly dangerous, which is exactly what led to the development of the Governor, or the droop compensator.
Okay.
This is a mechanical or digital system that senses changes in the rotor RPM and automatically adjusts fuel flow to the engine to maintain that strict, constant speed.
Okay, here's where it gets really interesting. Because the modern evolution of this is FADC, right? Full Authority Digital Engine Control.
Yes, FADC is the modern standard.
It's like a hyper-advanced cruise control. But instead of just reacting to a car slowing down on a hill, it's actively anticipating the load.
Exactly.
The text points out that FADE manages the turbine temperatures, the variable stator vanes, the bleed valves. I have to admit, though, I get a bit lost in the turbine mechanics here.
It is a lot to take in.
Yeah, like if the pilot suddenly yanks the collective, creating a massive spike in drag, how does the FADC instantly ramp up a jet engine's power without melting the internal components?
What's fascinating here is the sheer speed of the thermodynamics involved. A turbine engine is highly sensitive to the flow of air through its compressor section. If the FAD simply dumped a massive amount of fuel into the combustion chamber to instantly fight that sudden rotor drag, the sudden pressure spike in the combustor could push back against the incoming air.
And what does that do?
It causes a compressor stall, which is a violent, explosive rejection of airflow.
Oh, like a backfire, but inside a jet engine.
A catastrophic one, yes. To prevent this, while still delivering instantaneous power, the FADE manipulates variable stator vanes.
Stator vanes, what are those?
They are these tiny, adjustable airfoils inside the compressor section of the engine. The computer rapidly pivots these vanes in milliseconds, physically changing the angle at which the air is guided into the compressor blades.
Oh, wow, so it's directing the air on the fly.
Exactly. This ensures the airflow remains smooth and stable even as the engine accelerates violently. Simultaneously, it might open bleed valves to vent off excess pressure.
That's incredible.
It is. The pilot simply asks for lift, and the FADE performs thousands of calculations per second to deliver exactly enough power to keep the rotor speed perfectly constant without destroying the turbine.
So the pilot is never actually controlling the engine. The pilot is simply setting a demand for aerodynamic performance, and the digital brain is translating that demand into a perfectly regulated fuel flow.
Precisely. You are commanding lift, not power.
But that brings us to the physical plumbing of the aircraft. The FADE is perfectly managing a turbine engine that's screaming at, what, like 30,000 RPM?
Yeah, tens of thousands of RPMs.
Right. But the main rotor, to avoid those transonic shock waves, is locked in at maybe 300 RPM. How do you physically connect an engine spinning that fast to a rotor spinning that slow?
Through an incredibly robust transmission system. And this is a far cry from an automotive gearbox.
I would imagine so.
A helicopter transmission uses a series of complex planetary gear sets to step down that blistering engine speed to the usable rotor speed. We're talking about reduction ratios that can easily exceed 50 to 1.
50 to 1, that's massive.
It has to be. The main gearbox has to handle the sheer, violent torque output of the turbine, reduce the rotational speed, and then translate all of that twisting force 90 degrees upward into the rotor mast.
Which has to generate an insane amount of heat.
Oh, the friction and heat generated in this process are immense. It requires dedicated cooling systems just to keep the gears from welding themselves together.
Dealing with all that torque isn't just an internal mechanical problem, right? It creates an external aerodynamic crisis.
Yes, Newton's third law.
Exactly. Every action has an equal and opposite reaction. We know that when you apply massive torque to a mast to spin a heavy rotor clockwise, the fuselage of the helicopter desperately wants to spin counterclockwise. You need anti-torque. You need the tail rotor.
Right, you have to counteract that twisting force.
But our source text highlights a brutal inefficiency here. It notes that a conventional tail rotor consumes 10 to 15% of the engine's total power.
Yep, 10 to 15%.
It feels like an unacceptable parasitic loss. We are bringing fuel and stealing power from the main lift system just to stop the cabin from spinning in circles. Why do we accept that?
Well, this raises a really important question, and it's one that aerospace engineers have spent decades trying to design their way out of. The text actually details two highly sophisticated alternatives to the traditional tail rotor.
Okay, yeah. The first is the NOTAR system, right? An acronym for no tail rotor.
Exactly. NOTAR.
I've always been fascinated by NOTAR. If you don't have a vertical propeller in the back pushing against the torque, how are you stabilizing the aircraft?
It utilizes fluid dynamics, specifically something called the Coanda effect. Inside the root of the tail boom, driven by the main transmission, is a variable pitch fan.
Okay, so there is still a fan, it's just hidden.
Yes. And this fan pressurizes the hollow interior of the tail boom. Down the side of the boom, there are these precisely engineered longitudinal slots. The pressurized air is forced out of these slots, blowing downwards.
And how does blowing air out of a slot stop the helicopter from spinning?
Because of the massive downwash coming from the main rotor. As the main rotor pushes air down over this cylindrical tail boom, that jet of air exiting the slots causes the downwash to adhere to the curved surface of the boom.
Oh, I see.
Yeah, it essentially bends the airflow around the cylinder. This aerodynamic manipulation turns the entire tail boom into a vertical wing that generates lateral lift, pulling against the torque of the main rotor.
That is brilliant. You are literally using the waste air from the main rotor to generate horizontal lift on the tail.
Exactly. And a directed jet thruster at the very end of the tail boom provides the fine-tuned directional control for the pilot.
So it solves the problem.
Mostly. It eliminates the parasitic drag of an exposed tail rotor, it drastically reduces the noise signature, and it removes the physical danger of a spinning blade on the ground. However, managing the internal airflow and the structural weight of the fan system means it's still an aerodynamic compromise.
Of course. Which naturally leads us to the second, much more radical alternative in the text. Coaxial rotors. If the problem is torque, why not just build a system with absolute aerodynamic symmetry?
And that is exactly the philosophy behind aircraft designed by Kamov, or experimental platforms like Sikorsky's X-2. You mount two main rotors on top of each other, sharing the same vertical axis, but you gear them to spin in opposite directions.
Yeah. So one rotor spins clockwise, generating a counterclockwise torque reaction. The other spins counterclockwise, generating a clockwise torque reaction.
We've got it.
The two physical forces perfectly cancel each other out. There is zero net torque applied to the fuselage.
Precisely. You completely eliminate the need for a tail structure dedicated to anti-torque. That 10 to 15% power penalty just vanishes.
Wow.
Every ounce of horsepower generated by the turbine can be routed directly into vertical lift and high-speed forward thrust.
Right.
But the mechanical complexity of achieving this is staggering.
I can only imagine.
You have a hollow lower rotor mass spinning one way, with an inner upper rotor mass spinning the opposite way inside it. It requires dual swash plates and an impossibly complex web of pitch links to control the blades.
Right, because everything in aerospace is a trade-off. You eliminate the parasitic drag of the tail, but you buy yourself a mechanical nightmare in the rotor head.
Very much a mechanical nightmare.
But speaking of mechanical nightmares, I have to ask the ultimate contingency question.
Let's hear it.
We've established that staying in the air requires this delicate, digitally managed dance. The FADE is adjusting stator vanes. The transmission is wrestling with torque, all to keep the rotor speed perfectly constant. What happens when the turbine seizes?
The engine dies.
Right, the engine dies. The FADE key has no power to govern. I understand the emergency procedure is called autorotation, but I'll admit I'm a bit confused by the physics here. If the engine stops driving the mast, shouldn't the immense aerodynamic drag we talked about earlier just grind those blades to a halt in seconds?
It absolutely would, if not for a critical mechanical failsafe called the freewheeling unit, or sprag clutch.
A sprag clutch? How does that work?
The absolute fraction of a second that the engine's RPM drops below the rotor's RPM, this clutch disengages. It completely mechanically divorces the dead engine from the main transmission. The engine seizes, but the rotor is left free to spin on its own inertia.
Okay, so the engine isn't acting as a brake, but the pilot still has to act immediately, right?
They have less than a second to push the collective lever flat to the floor. They must instantly flatten the pitch of the main blades to strip away that massive induced drag.
And once they do that,
Once the drag is reduced, the helicopter begins to fall, and the aerodynamics of the rotor completely invert.
wait, invert how? Because normally the rotor is pulling air from above and violently shoving it downward to create lift.
Exactly. But in a rapid, controlled descent, the relative wind changes. Air is no longer being pulled down. Instead, because the aircraft is falling, massive amounts of air are rushing upward through the rotor disc from below.
So it turns into a windmill.
It does. The aerodynamics are incredibly elegant. That upward flow of air alters the aerodynamic vectors acting on the blade profile. It creates a forward-leaning resultant force.
Okay.
In a specific section of the blade, the driving region, the aerodynamic force actually pulls the blade forward, overcoming the drag of the tip and the root.
That is wild.
The engine is dead, no fuel is burning, but the upward rush of air physically drives the rotor, keeping that critical N right in the green operating band.
But maintaining rotor speed while falling only solves half the problem. You still have to, survive the impact with the ground.
Right, and that relies on the flare. At
Yeah.
the very bottom of the descent, mere feet above the ground, the pilot pulls the collective sharply up.
To catch the air.
Exactly. They are purposefully introducing massive drag to bite into the air, instantly trading the rotational kinetic energy stored in those spinning blades for a massive one-time burst of vertical lift to cushion the touchdown.
And this is where the text highlights a design detail that completely blew my mind.
The lead weights.
The lead weights. To ensure that flare actually works, engineers install physical lead weights inside the extreme tips of the rotor blades. We spend millions of dollars in aerospace engineering trying to shave grams of weight off airframes, and they are intentionally stuffing heavy lead into the tips of the wings.
It seems so counterintuitive until you look at the physics of rotational inertia.
Walk me through it.
The formula for the moment of inertia relies heavily on the distance of the mass from the axis of rotation. By placing dense lead weights at the very tip of a long rotor blade, you exponentially increase the rotor system's rotational inertia.
Oh, I see. So it acts like a heavy flywheel. Once it's spinning, it desperately wants to stay spinning.
Exactly. And it provides two massive survivability benefits. First, when the engine fails, that heavy-weighted rotor takes much longer to decay in speed, buying the pilot precious fractions of a second to react and lower the collective.
And the second benefit?
Second, a heavier rotor stores significantly more kinetic energy during the autorotative descent. When the pilot pulls the collective for the flare at the bottom, they have a much larger, more forgiving reservoir of energy to convert into lift.
But the structural trade-off must be terrifying. You have heavy lead weights spinning at hundreds of miles per hour. The centrifugal force trying to rip those blades out of the rotor hub must be astronomical.
Oh, the centrifugal loads are immense. It requires massive, heavily reinforced titanium grips and rotor masts.
Right.
It is a calculated compromise. You accept a heavier, beefier rotor head in exchange for a kinetic safety net that allows the crew to survive a catastrophic engine failure.
Wow. So what does this all mean? Let's bring this full circle. We started with the assumption that the throttle dictates the speed of the blades, and we've seen that it's entirely false.
Completely false.
A helicopter's throttle isn't dictating speed, it is dictating the capability to fight off aerodynamic drag. The digital brain, the FADEC, is constantly shifting stator vanes and bleeding pressure to ensure the rotor spins at one singular, non-negotiable speed.
Every component we've discussed today, the variable pitch blades, the massive gear reduction in the transmission, the fluid dynamics of the NOTAR system, and the heavy lead weights in the tips, they are all subservient to the strict aerodynamic boundaries of the rotor.
It's credible.
It really is an intricate, hostile environment managed by precise physical compromises. The next time you see a helicopter hovering or lushing overhead, you won't just see spinning blades, you'll see a masterclass in physics. A governor making microsecond adjustments, a transmission wrangling thousands of RPMs, and weighted blade tips ready to act as a kinetic safety net.
It fundamentally changes how you view the machine. But before we sign off, I want to leave you with one final thought to ponder.
Go for it.
We've spent this time exploring the immense mechanical complexity required purely to manage a traditional combustion turbine engine. We need FAD to prevent compressor stalls. We need 50-to-1 planetary gearboxes to reduce RPMs. We need tail rotors to fight the torque of those massive internal moving parts.
It's a lot of engineering just to manage the engine.
Right. But as the world looks toward electric aviation, the physics shift entirely. Electric motors don't suffer from compressor stalls. They don't need to spool up. They can adjust torque instantaneously, with virtually zero mechanical lag.
That's a huge shift.
It makes you wonder, if we completely remove the mechanical constraints and the rigid RPM lag of a jet turbine, will the helicopter of the future even look like a helicopter anymore? Or are we standing on the edge of an entirely new shape of vertical flight? Thank you for joining us on this deep dive. Keep looking deeper into the everyday miracles of engineering around you.